So check this out. Astronomers have discovered an exoplanet they're calling Super Saturn. It's got rings over an AU wide. An AU is the astronomical unit, the distance between the Sun to the Earth. That's an incredibly huge ring system, hence its name. Super Saturn is being called Mamajek's object after the astronomer who led the team to whom we owe the discovery. Professor Eric Mamajek of Rochester University in New York found Super Saturn while scouring through data downloaded from wide-angle transit observations. WASP is the acronym for Wide Angle Search for Exoplanets. It's an ingenious project developed in the year 2000 by astronomers at Queen's University in Belfast, Northern Ireland, and St Andrews University in Scotland. Using 4 telescopes, the CCD video cameras on the scopes record the slight dimming of starlight caused by objects passing in front of stars. This is called the transit method of exoplanet detection. So, for example, the planet Venus transits across our view of the Sun every couple hundred years. A black dot, the silhouette of Venus, is visible, crossing in front of the Sun as Venus passes between our line of sight and the Sun. This tiny eclipse causes the amount of sunlight coming to Earth to be reduced by a minuscule amount, also known as teeny tiny. The same is true for all the stars in the Milky Way that have planets going around them. Exoplanetary transits in front of stars must be in direct line of sight with Earth for the starlight to be dim. Such transits do not occur very often. That's why thousands of stars must be looked at simultaneously for as long of a duration as possible, between 4 and 8 hours a night. WASP was created to stare continuously at as wide of a range of stars as possible. Maybe one of them would show an exoplanet transit. That translates into a lot of data being produced, about 40 gigabytes per viewing session. Computer scientists at Leicester University in England developed a computer program to store the data and generate photometric graphs of the light intensity of each star. Open University, also in England, joined the WASP project, took this data, and made it available for research by astronomers worldwide. The graphs of the intensity of starlight show that changes in its brightness are called light curves. These graphs have 2 axes. One is in the timeline axis, the other one is the intensity of light. As the object, considered an exoplanet, though it could also be a brown dwarf star, crosses in front of the star, the timeline axis keeps track of how swiftly it is moving. It tells us how close the object is to the star, while the brightness axis keeps track of how much the starlight dims. This way, we can find out how large the object is. Now, obviously, big objects will dim the light more and be easier to detect. At present, Earth-based equipment is not sensitive enough to measure the dimming caused by planets as small as Earth. Neptune's size and larger ones are the limit for WASP. However, the James Webb Space Telescope, which is now in operation, has a much greater sensitivity and will be able to resolve the transits of Earth-sized exoplanets. Now, I know you want me to get to Super Saturn, but there's something else you should be familiar with before we get there. If the exoplanet has an atmosphere, or, in the case of Super Saturn, a ring system, the starlight from the star the planet is transiting will shine through the atmosphere or ring system, and that can be detected too. The light curve will show less dimming in the photometric data, because not all the starlight is being blocked. Some light is still getting through the atmosphere or rings. This is important because it gives astronomers a reading of the atmosphere. The James Webb Space Telescope is fitted with spectroscopes that can determine the gas content of the transiting exoplanet atmospheres: oxygen, methane, carbon, etc. The WASP project has been really catching on. There's a Super WASP project now consisting of WASP North and a WASP South. One looks at the sky above the northern hemisphere, the other looks at the sky above the southern hemisphere. There's also a Next Generation Transit Survey, NGTS, based on the WASP project. It's automated, so astronomers don't have to stay up all night sipping coffee, but they can if they want to. Located at the European Southern Observatory in the Atacama Desert in Chile, the NGTS scans millions of stars and has discovered over 100 exoplanets, down to a size as small as 3 times the size of Earth. NGTS has started a Planet Hunters Club on social media. Citizen scientists can search the online database of light curves and perhaps discover your very own exoplanet. What had been a strictly British effort started by 1 or 2 astronomers is now a worldwide phenomenon. With the ability to read the spectroscopic signatures of atmospheric gases during exoplanet transits, a new idea emerged: technosignatures. That is, specifically identifying gases in exoplanet atmospheres that are produced by civilizations. The James Webb Space Telescope can do this. Gases from pollution, such as chlorofluorocarbons (CFCs), can be seen spectroscopically if present. Tritium from fusion reactions, if they have them, can also be detected, along with heat patterns from cities on the planet's surfaces. Technosignatures is a recent concept that originated after the WASP project started. Who knows what it will turn up? Now let's get back to Super Saturn. The star that Super Saturn orbits is J1407, a small, dim, sun-like pre-main sequence star of the 13th magnitude. Huh? Well, the human eye can only see stars to about the 6th magnitude, and each magnitude is 2.5 times dimmer than the previous one. So it's not an exceptional star, just another telescopic star out there in the Scorpius-Centaur region of the night sky. J1407 is a young star that hasn't yet settled into its stable, long-duration phase. This is important because Super Saturn, officially J1407b, is showing signs of having a ring system in an early stage of development. Super Saturn's light curve was tucked away in the mountain of data from the Super WASP project. Professor Eric Mamajek and his associate Matthew Kenworthy of Leicester University studied the data thoroughly and produced a detailed report on it. Knowledge depends on good data. The horizontal axis of J1407b's light curve, the time axis, is what's causing all the hubbub. It took Super Saturn weeks to transit across in front of its parent star, 56 days to be exact. Planetary ring systems that we are familiar with in our solar system orbit right around the equators of the gas giant planets and are very thin, from only a few meters thick down to a few centimeters. In a telescope, Saturn's rings will seem to disappear when the planet is at zero inclination toward Earth. Saturn must be inclined at an angle in relation to Earth to see Saturn's beautiful ring system. It's something everyone should make a point of seeing: Saturn in a telescope. If Super Saturn's rings block most of the light from J1407 for 56 days, it means that the planet had to be orbiting at a steep inclination to its star. If it were at zero inclination, we wouldn't see the rings blocking any light. Therefore, the orbital time could be determined 10 years minimum to 200 years if the orbit is highly elliptical. The superplanet itself is calculated to be 24 times the mass of Jupiter, which means that if it is gaseous, it could be a brown dwarf star. Super Saturn appears to have a Mars-sized object orbiting around it, because there is a huge gap in the rings that was most probably cleared out by a large object. The Cassini division in the rings of Saturn is where the moon Mimas has cleared out a path through Saturn's rings. The light curve of Super Saturn has only been observed once. All the exoplanet detection systems are keeping an eye out for it to come back around J1407. No one knows when that will occur. Some astronomers have suggested that J1407b is a brown dwarf star system in itself, merely passing in front of, but not connected to, star J1407. An orbital reappearance of Super Saturn would disprove that conjecture. The center region of Super Saturn blocked out all the light from its primary star. This is what indicates that the ring system is new and in an early developmental phase. Over time, the very dense ring mass close to the planet is expected to thin as all this matter gets absorbed into the planet or ejected into space. This is what has happened with our solar system's gas giant planets. The Mamajek object is a shocker. Never before or since has a light curve been detected like Super Saturn's. Super Saturn has added a new chapter to our understanding of the formation of ring systems. So, here's to you, Super Saturn. Hope to see you again soon. So, planets with two suns, like Tatooine from Star Wars, used to sound like pure fantasy. For decades, scientists believed these systems were too unstable to exist. Two stars tugging at a planet should fling it into space or drop it into one of the suns. Except, it turns out that nature didn't get the memo. Astronomers have found a planet calmly orbiting two stars like it's no big deal. This planet lives closer to its two parent stars than any other directly imaged planet in a binary star system astronomers have ever seen. Now, direct imaging means they saw the planet's light, not just its shadow. The whole system sits about 446 light-years away, so the light we see from it today left before humans ever built modern cities. This space monster is roughly 6 times the mass of Jupiter. And even more surprising, the planet is only about 13 million years old. That sounds ancient until you zoom out a little. Earth is about 4.6 billion years old, which makes this planet basically a newborn in cosmic terms. The two suns of this monster orbit each other incredibly fast and complete a full loop in just 18 Earth days. That means their gravity constantly shifts, yanking space around them like a cosmic washing machine. Even so, the planet stays locked in its path, so it takes it 300 Earth years to finish a single orbit. So nobody fully understands how this planet formed in the first place. When two stars orbit each other this closely, their gravity usually tears apart planet-forming material before anything big can take shape. Scientists have only found a few dozen planets like this so far, and that's nowhere near enough to piece together the full story. To solve the mystery, they need more data. Now, another cool find that still needs more research is a planet so stretched by gravity that it looks like a lemon, not a sphere. This planet is nothing like the calm blue and green worlds we see in space movies. It orbits a pulsar, which is basically a star's corpse. When a massive star expires, it collapses into an ultra-dense object that spins insanely fast and blasts radiation like a cosmic lighthouse. Being near one of those means game over for anything solid. And yet, this planet hangs on, barely. The gravity stretches it, pulling harder on the side facing the pulsar than the far side, like cosmic taffy. And here's where it gets extra unsettling. When scientists analyzed this planet's atmosphere, they didn't find water or oxygen. They found helium and pure carbon. No clouds, no oceans, no chance of life. According to everything we know about planet formation, this world shouldn't exist at all. So it might not be a planet in the normal sense. It could be the exposed core of a star that got shredded, leaving behind something stuck between planet and stellar corpse. That's a pretty scary trend. The line between planets and stars keeps getting blurry. And speaking of scary, meet this guy. This system lives around two red dwarf stars. These two stars orbit each other at a distance similar to how far Jupiter sits from the Sun. Scientists found two Earth-sized planets and a third possible one squeezed right up next to the stars. One planet completes a full year in just over 2 days. Another takes about 3.5 days. The candidate planet orbits even faster. To put that in perspective, these planets sit less than 2 million miles from their star. The Moon sits about 250,000 miles from Earth. So yeah, these worlds are close. When they combined data from space and ground-based telescopes, astronomers realized they were staring at something totally new – planets that transit or pass in front of both stars. Most planets in double-star systems orbit only one star, and this setup shouldn't last long according to the rules of physics. But these planets exist anyway, calmly breaking the rules. So this guy proves that planet formation works in ways we still don't fully understand, and space clearly enjoys messing with our expectations. Now, let's crank up the horror a notch. Astronomers made the first ever 3D map of a planet outside our solar system. And not just any planet. This one is so hot it literally tears water molecules apart. As the planet moved behind its star, the James Webb watched tiny changes in the star's light at different colors or wavelengths. Some colors get absorbed by water vapor, others don't. By stacking all that info together, scientists figured out temperatures at different heights and locations in the planet's atmosphere. And that's how they learned that parts of its atmosphere heat up to nearly 5,000 degrees Fahrenheit, hotter than molten lava. This superhot planet sits about 400 light-years away and weighs around 10 times as much as Jupiter. It races around its star in just 23 hours. 1 year there is basically a day. And because it's so close, the temperatures get so high. Winds try to move heat around, but they totally fail. WASP 18b's atmosphere barely has any water and instead overflows with carbon monoxide. Astronomers once believed water should be common in giant planet atmospheres. This world proves water is optional, not guaranteed. Now, magma worlds are another perfect proof of that. There's a huge group of planets called sub-Neptunes, planets bigger than Earth but smaller than Neptune. For a while, some scientists hoped these worlds were Haitian planets, covered in deep oceans of water or ice, wrapped in thick atmospheres. One famous example was K2-18. Its atmosphere showed methane and carbon dioxide, but almost no ammonia. But as it turned out, lava dissolves ammonia too, so the missing ammonia doesn't prove water at all. It could just mean the planet has a global ocean of magma instead. The researchers modeled how these planets heat up, cool down, and evolve over time. They asked a simple question: do these planets ever cool enough to stop being lava worlds? And the answer was almost never. When they tested thousands of known sub-Neptunes, they say almost all of them are likely lava worlds, not water worlds. In simple terms, these planets don't breathe water vapor, they breathe rock vapor. Their atmospheres come from magma boiling, not oceans evaporating. And that changes everything. Many worlds we once labeled maybe habitable turn into hellscapes the moment you run the numbers honestly. And that means space isn't hiding Earth clones, but mass-producing furnaces and other sorts of monsters. Take this bad boy, for instance. It sits only about 64 light-years away, which is uncomfortably close in cosmic terms, and it's the nearest hot Jupiter to Earth. From afar, it looks stunning, a smooth, deep blue marble floating peacefully in space. But that color hides something absolutely brutal. On this planet, it rains glass, sideways. Winds scream across the atmosphere at around 5,400 miles per hour, fast enough to shred anything instantly. The blue color comes from tiny particles of silicate, the stuff glass is made of, floating in the air. The planet's surface temperature hits about 2,400 degrees Fahrenheit, hot enough to melt rock. That heat turns those silicates into microscopic shards of glass that whip around the planet like a worldwide sandblaster. Standing there wouldn't hurt. You wouldn't exist long enough to ever feel it. And then there's the darkest planet ever found. It reflects less than 1% of the light that hits it. It's darker than coal, darker than black paint. Light just disappears into it. Not all planets even bother with stars at all. Astronomers have found rogue planets, worlds kicked out of their solar systems. These lonely planets drift through space in total darkness, frozen and untethered, with no sunrise ever again. Now, all of this shows us that our universe isn't designed for life. Life survives despite the universe, not because of it. Earth isn't typical, it's lucky. We're only at the beginning of this discovery era. Every year, new telescopes sharpen the picture, and every year, the picture gets stranger. The more clearly we see the universe, the less it resembles our imagination. And that's the most unsettling truth of all. Okay, see that tiny dot in the dark sky? Squint. Still nothing? No wonder. Even though it's very close to Earth in cosmic terms, it's still 18 light-years away from us. But one day, this distant world you can't see with the unaided eye might become a new home to us, because it likely has all the right stuff for life. They're calling it GJ251c, and it's a super-Earth. Now, a quick side note. Super-Earth sounds epic, but it doesn't mean it's some fancy version of Earth with superpowers. It just means it's bigger, somewhere between Earth and the gas giants like Neptune. These planets can be rocky, gassy, like me, or a mix of both. The super only refers to size, not whether you could actually spend your vacay there. Now, this planet sits perfectly in what scientists call the Goldilocks zone. It's not too hot, not too cold, just right for liquid water to hang around. And where there's water, there could be life. We're talking about at least some weird bacteria with serious survival skills. Of course, scientists are still trying to crack the code of what actually makes a planet come alive. There's a whole mix of conditions: distance from the star, atmosphere, and temperature, and GJ251c looks like a top contender. The first thing astronomers check when they stumble across a new super-Earth is if it's rocky like Earth or just another ball of gas like Neptune. Because so far, Earth's still the only rocky world we know that actually supports life. And second, could liquid water exist there? Because water is the ultimate life ingredient. Finding a planet that checks both boxes is super rare. Out of the thousands of exoplanets discovered so far, only a tiny handful hit that sweet spot. So when astronomers realized GJ251c might be one of those, and that is just 18 light-years away, well, they got pretty hyped. The planet star GJ251 is a red dwarf, a small, cool star about 1/3 the size of our Sun. Because red dwarfs don't put out as much heat, their Goldilocks zones are close in, which actually makes planets easier to find. They whip around faster, so scientists can pick up their orbital patterns more easily. Scientists have been keeping an eye on this star for a while, having collected over 2 decades of data. They already knew it hosted one planet, GJ251b, another super-Earth that orbits every 14 days. But sadly, it's way too close to the star to be habitable. But then, digging deeper into the data, the team spotted hints of another world. It was GJ251c. This one looked promising. So astronomers started watching how the star itself wobbled slightly. Those tiny shakes happen when planets tug on their stars with gravity. The bigger the planet, the harder it pulls. Unexpectedly, the researchers didn't just see the signal from the known planet, GJ251b, there was another tug. GJ251c circled its star every 53.6 days. Now, the catch is, we still don't know much about this new world. We got its mass, sure, about 3.8 times heavier than Earth, but since it doesn't cross in front of its star, we can't tell how big it is or what it's made of, yet. Basically, we found its gravitational footprint, but not the planet itself. Still, astronomers are excited. The new world is bright, close, and perfectly placed for future missions to actually see it directly. That's like going from hearing a noise in another room to opening the door and seeing what's making it. Now, at the same time, that kind of direct imaging is incredibly hard. Stars are bright, and planets are tiny faint specks right next to them. But the new generation of telescopes, the big ones being built right now, might finally have the tech to pull it off. For now, the team's being cautious. The discovery looks solid, but they want to confirm it with even sharper instruments. The next step might literally be seeing this world with our own eyes, well, through a billion-dollar telescope. But for now, it's a really promising mystery world. It's just a matter of looking closer. But let me tell you another thing, and I bet you didn't expect anything like this. Even if another civilization existed on GJ251c or some super-Earth, they might be totally stuck at home. A new study suggests that for all their fancy tech, they'd have a seriously tough time getting off the ground. And I mean it literally. The problem? Gravity. It's a total spoil sport. The thing is, super-Earths are way bigger and heavier than our planet. As a result, their gravity pulls a lot harder. And when gravity cranks up, so does the fuel bill. It skyrockets, pun intended. Launching a rocket from one of those worlds would take exponentially more fuel than it does here on Earth. On a planet that's about twice Earth's radius, the mass can jump to roughly 10 times that of our home planet. That means gravity could be more than twice as strong as what we feel on Earth. Think weighing 300 pounds instead of 150, just by standing there. Ew. Now, this extra gravity isn't all bad. It helps keep a thicker atmosphere, which means better protection from cosmic rays and radiation. That's great news if you're a microbe trying to evolve without getting zapped every few minutes. The thicker air could also help regulate temperature and even support more complex weather systems. So, for life starting out, that's a big thumbs up. But when it comes to building rockets, it's a total nightmare. That same gravity that holds the atmosphere also chains you down. For example, let's take Kepler 20b, a super-Earth about 1.87 times Earth's radius and 9.7 times its mass. There, a chemical rocket trying to launch just 1 ton, which is about the weight of a small car, would have to be 3 times the size of the Saturn V, and that's the biggest rocket ever built, which carried about 45 tons to the moon. Even if our hypothetical super-Earth inhabitants were smart enough to dream of space travel, they'd quickly run into a gravity-sized problem. Sure, they might try to build launch pads high up in the mountains to shave off some of the crushing gravity. But on big planets, mountains don't get tall. The immense gravity just squashes them down before they can grow sky high. Oh, by the way, that's why the tallest peaks in our solar system aren't on the big planets at all. Mars, which is quite a lightweight world, hosts Olympus Mons, a volcano that towers 13.5 miles high. But on a much heavier planet, mountains that tall would collapse under their own bulk before the rocket builders even got halfway up. So, our poor super-Earth engineers would probably need to build massive artificial launch towers just to get closer to thinner air. If they had flight technology, like airplanes or helicopters, they might try flying their rockets up first and then lighting the engines in midair. We're actually inching towards something like that on Earth with air-launched rockets. But what if that planet was a water world, and a lot of super-Earths might be? In that case, their smartest species might not even live on land. They easily could be aquatic geniuses. Picture dolphin-like engineers or squid astronomers, forced to launch rockets from underwater. Kind of ballistic missile submarine-type space launches. But even with all that effort, the physics is still tough. For a super-Earth about 10 times Earth's mass, chemical rockets could technically work, but the cost would be ridiculous. You'd need so much fuel that you'd have to burn through a sizable fraction of the planet just to get one ship into orbit. The only real options for super-Earth civilizations might be nuclear-powered rockets or space elevators made of materials stronger than anything we've discovered. Until then, those creatures might stay stuck on the ground with no satellites, no space stations, and no super-Earth NASA. So, as our telescopes keep spotting new, potentially habitable worlds, we probably shouldn't expect to find any weather satellites circling above them. If there's life out there on the super-Earth, it's likely gazing up at the stars, wishing it could visit them, just like we once did. Our universe is starting to glitch, and it looks like we're going through the biggest tension in astronomy since Einstein redefined gravity. But scientists aren't having a cow yet, because this kind of chaos usually means we're about to discover something huge. So let's run through the biggest issues driving the crisis. For decades, cosmology ran on the idea that the universe should look uniform in all directions for anyone anywhere within it. They call this idea the basic cosmological principle, not to be confused with the cosmetological principle, which states all women should wear a color of lipstick right for them. But I digress. Cosmologically speaking, it means you might see clumps up close, but on massive scales, everything should smooth out. Because of that, scientists figure no structure should be bigger than about 1.2 billion light-years. Yeah, that's big. So they were more surprised to find a structure called the Big Ring. This thing is nearly a perfect circle made of galaxies and galaxy clusters, and it's about 1.3 billion light-years wide. Now, a light-year is the distance light travels in a year, and since light is the fastest thing in the universe, that already tells you how enormous this distance is. If your eyes could see it, it would stretch across the sky like 15 full moons lined up side by side, see? And the Big Ring isn't alone. A couple of years earlier, the same astronomer spotted something called the Giant Arc, a curved structure stretching 3.3 billion light-years. Then there's the giant GRB ring, found in 2015, with a mind-melting diameter of 5.6 billion light-years. The Big Ring and the giant arc show up in the same part of the sky at about the same distance from Earth. So there's a real chance they're actually parts of an even bigger structure hiding in plain sight. Now, another scientific drama has to do with something called the Hubble constant. That is, how fast the universe expands, the connection between how far away an object is and how fast it's moving away from us. That number helps scientists figure out the age, size, and future of the universe. The Hubble Space Telescope determined that number with an accuracy of almost 1%. The universe is about 13.8 billion years old. So there was Hubble, and later the James Webb Space Telescope that measured distances to faraway galaxies and figured out how fast they're moving away from us. In everyday terms, they showed that for every million light-years you go out into space, galaxies move away about 45 to 47 miles per second. That expansion speed lines up nicely with a universe that's 13.8 billion years old. But there's another totally different way to measure the universe's expansion, and it looks way further back in time. Scientists study the cosmic microwave background, or CMB, which is the leftover heat from the Big Bang. It's the oldest light in the universe, released when the universe cooled enough for light to travel freely. When scientists use the CMB to calculate how fast the universe should be expanding, they get a slower number, about 42 miles per second per million light-years instead of 45 to 47. Now, that might not sound like much, but in cosmology, that gap is enormous. Both methods are extremely precise, and yet they stubbornly refuse to agree. This disagreement has a name, the Hubble tension. Right now, nobody knows why this is happening. Something might be missing from our understanding of the early universe. Now, just when astronomers thought it couldn't get stranger, the James Webb Space Telescope kicked the door down. It spotted some impossible early galaxies. These galaxies show up just 500 to 800 million years after the Big Bang. According to everything we thought we knew, galaxies at that age should look messy, small, and half-finished. But instead, Webb keeps spotting galaxies that look like they've had billions of years to grow up. They already show organized shapes like disks and bulges, basically the same structures you see in modern galaxies like the Milky Way. Features like that should take several billion years to form, not a few hundred million. It's like meeting a teenager who somehow has the wisdom of an 80-year-old. Now, in some cases, smaller galaxies seem to pack more mass than bigger ones, which also completely flips our expectations. Even cooler, some of those early galaxies contain heavy elements like oxygen and carbon. Stars make those elements, but stars need time to cook them up through nuclear fusion. Seeing heavy elements like that early is like finding baked bread before anyone invented ovens. Either the universe evolved way faster than we thought, or our timeline is missing entire chapters. Another weird headache in cosmology is all about lithium. Yep, the same element in phone batteries. According to the Big Bang idea, the early universe was insanely hot and dense, hot enough to smash particles together and create a tiny amount of lithium. Not much, but enough that we should still see about 5 lithium atoms for every 10 billion hydrogen atoms floating around today. Astronomers can actually check this by looking at stars. They use a trick called spectroscopy, which means splitting starlight into colors to see what elements are inside. Now, to estimate a star's age, they look at iron. Iron only forms in supernova explosions, so stars with very little iron are super old, born when the universe was still young. But here's the problem. Those ancient low-iron stars barely have any lithium. Not just a little less, sometimes less than 1/20th of what the Big Bang predicts. And the older the star, the worse the mismatch gets. Scientists call this mess the lithium problem, and it's been haunting cosmology for decades. Some researchers tried to explain it by saying stars somehow destroy lithium internally. But every version of that idea crashes into other observations. Instead of getting better, the problem keeps getting worse. And when a simple element refuses to behave, it usually means our picture of the early universe still misses something big. Well, dark matter adds another dark spot to the picture. Scientists invented it to explain why galaxies don't fly apart. It acts like invisible glue. Models predict dark matter should pile up densely in galaxy centers and form sharp spikes. But observations keep showing smooth, soft cores instead. It's like expecting a mountain peak and finding a gently rolling hill. That mismatch shows that dark matter isn't behaving the way scientists assumed at all. Some of them even suggest dark matter might feel a fifth force, something beyond gravity, electromagnetism, and other known forces. That idea sounds wild, but it neatly explains why dark matter spreads differently than predicted. If it turns out to be true, it would change how we perceive the way galaxies form, how they evolve, and how the universe structures itself on every scale. And finally, there's dark energy that has confused scientists ever since they stumbled on it about 25 years ago. It makes up most of the universe, and we still don't know what it is. The default idea said dark energy stays constant, like a built-in pressure of empty space itself. Some theories linked it to quantum fluctuations, which are tiny particles popping in and out of existence in empty space. But when scientists calculated how strong that effect should be, they got a value trillions upon trillions of times too big. So clearly, something didn't add up. Now, a massive project shows that dark energy might not be constant after all. Instead, it might have peaked about 4.5 billion years ago and slowly weakened since then. If that's true, dark energy changes over time. Why does this matter? Because dark energy controls the universe's future. If it stays strong, the universe keeps expanding faster and faster until galaxies drift so far away we can't see them anymore, a scenario called the Big Freeze. If dark energy weakens enough, gravity might slowly fight back, expansion would slow, and galaxies that are currently disappearing could drift back into view. All these problems share something unsettling. They're systematic. They repeat across instruments, methods, and research teams. Random errors don't behave this consistently. The universe keeps giving conflicting answers, no matter how carefully scientists ask the questions. That's why researchers call this a crisis, not because science failed, but because it's working exactly as it should by revealing where our ideas fall short.
An ultra-powerful explosion happened just outside the Milky Way galaxy, kinda next door in cosmic terms, and it was unlike anything we've witnessed before. The thing kept blasting again and again, shooting out crazy strong bursts of energy called gamma rays. It was almost an entire day of non-stop firing back in July 2025. In gamma ray time, that's basically forever, because normally gamma ray bursts last from a few milliseconds to a few minutes, not hours on end. But the craziest thing is that this phenomenon might be linked to an elusive and mysterious kind of black hole, the existence of which we haven't proven yet. Scientists gave this phenomenon a complex sciencey name. Usually, these gamma ray bursts happen when a giant star goes off. One big dramatic exit, and that's it. But this space diva didn't get the memo and kept coming back for encores. NASA's Fermi telescope first spotted this bizarre space performance on July 2nd. But then some other space gear, the Einstein probe, realized it had already been blasting the day before. Scientists tossed around a few guesses. It could have been a massive star, like 40 times the size of our Sun, that went out in a special kind of way. Not your average star demise, but one that somehow kept its cosmic engine running, like a car that won't stop even after the gas runs out. Another theory is even wilder. Some scientists think those space fireworks might have gone off when a star, likely a tiny one called a white dwarf, got shredded by a black hole. It's like a cosmic blender moment. They call it a tidal disruption event, or TDE. You see, not every star goes out with a giant boom like in the movies. Most just get old, puff up, and slowly fade away, leaving behind their tired little cores. Those leftovers are called white dwarfs. star corpses made of super weird squished up gas. You see, what happens to a star when it goes off depends on how big it was when it was born. Stars that start out kind of small, about the same size as the Sun or up to 10 times bigger, usually end up as white dwarfs. Most of the time, these stars run out of fuel and blow off their outer layers, creating a glowing cloud called a planetary nebula. What's left behind is the super hot dense core, about the size of Earth. That's the white dwarf. They're still really hot when they form and slowly cool down over time. After billions of years, they might turn into cold, dark, black dwarfs. But the universe isn't old enough for any of those to exist yet. Anyway, let's get back to our investigation. If this second theory is right, the black hole responsible for this cosmic show wasn't a regular one. To pull off something like this, it would need to be a super rare kind of black hole. One of those mysterious intermediate mass black holes scientists have been trying to find forever. Before we move further, let's take a look at the black hole lineup. Small ones are called stellar mass black holes. They're formed when massive stars weighing somewhere between 20 to 100 suns collapse. Supermassive black holes are real space behemoths. They're millions and even billions of times heavier than the Sun. They chill at the centers of galaxies. Even our home Milky Way galaxy has one called Sagittarius A star. This black hole is mostly dormant. It absorbs gas or dust only occasionally, but its estimated mass is millions of times that of our Sun. There might be one more type of black hole: primordial black holes. Scientists think they might have formed in the very first moments after the birth of the universe. That's when pockets of hot material could be dense enough to form black holes. Their masses might have ranged from 100,000 times less than a paperclip to 100,000 times more than that of the Sun. After that, the universe expanded and cooled very fast, and the conditions for forming black holes this way came to an end. These days, 13.8 billion years later, astronomers still haven't found definitive proof that those primordial black holes even existed. On the other hand, it's possible that they could have evaporated as space became older, due to certain processes happening at the edges of their event horizons, aka the points of no return. According to theoretical predictions, lower mass black holes with less mass than a mountain could evaporate more quickly than larger ones. If this idea is correct, then many of those early black holes have already completely dissipated. But more massive primordial black holes could still be lingering across the universe. Anyway, if we get back to the already proven kinds of black holes between stellar-sized black holes and supermassive ones, there are elusive intermediate mass black holes. Scientists think they exist, but they're like Bigfoot. Lots of theories, not much proof. Astronomers think that small black holes might crash into each other and merge over time to form those medium ones, but spotting one is almost impossible. They're sneaky and silent. People often tend to mistake them for star graveyards, clusters of smaller black holes just hanging out. Sometimes, intermediate mass black holes even hide behind groups of stars that orbit them real close. The best way to catch such a black hole is to look for clues. Scientists measure the mass of black holes when they crash into each other, or spot them mid-meal when they're munching on a nearby star. So far, around 300 possible intermediate mass black holes have been found, but no one is totally sure which ones are the real deal. And now, astronomers think they've finally caught this super rare missing link black hole. Right now, it might be snacking on a poor star way out at the edge of some distant galaxy. In a study published on April 11, 2025, scientists talk about a black hole called HLX-1. It's hanging out about 40,000 light-years from the center of its galaxy and roughly 450 million light-years away from us. Using data from NASA's Hubble Space Telescope and the Chandra X-ray Observatory, the team spotted a bright flash, that very tidal disruption event that occurs when a black hole tears a nearby star to pieces. Then they ran computer simulations to recreate the whole thing, and it showed HLX-1 stretching the poor star like space spaghetti. By the way, this process is indeed called spaghettification. Astronomers have their own cosmic jokes, you know? Anyway, scientists first spotted something weird going on with HLX-1 back in 2009. NASA's Chandra X-ray Observatory caught a super bright glow coming from deep space. Turns out, it could have been another tidal disruption event. The glow from HLX-1 hits its peak around 2012, and it's been fading ever since. But of course, there's a catch. Nobody's totally sure it's a real intermediate mass black hole. You see, that light might not be from a shredded star at all. It could be from an accretion disk, a giant, super hot ring of gas and dust swirling around the black hole's edges. And the only way to figure out what's really going on is to keep watching. If the light keeps fading and doesn't flare back up, then yeah, that poor star probably got eaten. Intermediate mass black holes are a big deal because they're the missing link in the black hole family tree. The connect the dots piece in understanding how black holes grow up. There's also an idea that intermediate mass black holes might start out as big stellar mass black holes and just keep bulking up over billions of years until they become those massive, city-sized monsters at galaxy centers. That means most of their lives, they're probably lurking way out on the galaxy's edge. Like HLX-1, before they get launched into deep space. And now, some scientists think there could be a sneaky intermediate mass black hole hanging out on the outskirts of our Milky Way right at this moment. Even if there isn't, the research team is still keeping an eye on what's happening after that blast and trying to piece together what in the universe actually caused it. Next up on their to-do list is figuring out exactly where it happened. Once they pin down the location, they'll be able to measure just how much cosmic energy this thing pumped out and how big the explosion really was.
A recent shocking discovery, shocking I tell you, shows that one galaxy can devour another smaller one, leaving behind just faint remains. Can anything like this happen to our home Milky Way galaxy? And if it does, what will happen to the inhabitants of the planet Earth? You know, us. Well, let's figure it out. This whole discovery is actually a curious story. Even before the Rubin Observatory, an astronomical observatory in Chile, even started its full science work, it accidentally helped astronomers spot something totally unexpected. In June, the team released its very first test images, and one of them showed a deep look at the Virgo cluster. That's a huge group of nearby galaxies scientists have been studying for years. But in the bottom right corner of that image, there was something thin and strange, and it wasn't me. It was a tiny razor-sharp streak of stars stretching away from a well-known galaxy called M61. No one had ever seen it before. Now, M61 looks a lot like our own Milky Way galaxy. It's a barred spiral galaxy with long, sweeping arms. But despite the similar shape, the center of M61 is far more dramatic. While Milky Way's supermassive black hole sits quietly, almost as if it's asleep, M61's black hole is wide awake and hungry. It feeds on surrounding matter and blasts out powerful flows of energy, which creates a kind of galactic storm that spreads through the galaxy. M61 has been studied for decades, but Rubin's camera is built to pick up things that are extremely faint. That's why this new star system suddenly appeared. It was as if someone turned on a flashlight in a dark room. Now, the stream is enormous. It's about 50 kiloparsecs long, which is roughly 163,000 light-years. That's more than the size of the entire Milky Way. Most stellar streams around our own galaxy are only a few tens of thousands of light-years long, so this one is huge by comparison. Scientists think that the long trail is made of a dwarf galaxy that got too close to M61. Once it crossed into the larger galaxy's territory, the dwarf galaxy became trapped in its gravitational grip. Little by little, powerful tidal forces began pulling it apart, stretching it into a long, faint trail of stars. Eventually, it was completely ripped apart by M61's gravity. When that happened, the larger galaxy seemed to have responded with a burst of new star-making about 10 million years ago. It almost felt like the collision kicked it awake. This process, large galaxies tearing smaller ones apart, is thought to be one of the main ways galaxies, like the Milky Way and M61, grow over billions of years. Each smaller galaxy that falls in becomes fuel for the larger one, adding stars and gas, and sometimes this process can even stir up activity around the central black hole. Will our Milky Way become that smaller galaxy one day? Well, we do have a much bigger neighbor, the Andromeda Galaxy. But at the moment, we can't predict whether it'll get hungry enough to attack the Milky Way. Whew, what a relief. Anyway, it might seem weird that the M61 stream had gone unnoticed for so long. It wasn't exactly faint or subtle, glowing with the light of about 100 million suns. Hard to miss. But it managed this trick by staying hidden behind a nearby galaxy. This makes it really difficult to detect even bright stellar streams. To find them, we need extremely sensitive instruments and careful techniques. At least now we know that giant galaxies may grow by eating smaller ones, leaving long trails of stars behind as evidence. The researchers admit that it's surprising that such a huge structure stayed hidden around a famous galaxy for so long. And it seems that the discovery of the M61 stream is just the beginning. The night sky might start filling with new uncovered structures, ghostly trails, forgotten galaxies, and the remains of ancient cosmic encounters. The Rubin Observatory is a brand new astronomy center built on a mountain in Chile. Its full name is the Vera C. Rubin Observatory. It was named after the astronomer who first found strong evidence that dark matter is real. Now, what makes Rubin special is that it's the first telescope of its kind. Its giant mirrors, super-sensitive camera, fast movement, and powerful computers all use cutting-edge technology. The main telescope, called the Simony Survey Telescope, has a 27-foot mirror, and it uses the LSST camera, which is the biggest digital camera ever made. But we'll talk about it a bit later. For 10 years, this telescope will take extremely detailed pictures of the southern sky. It will scan the entire sky every few nights, creating a huge, high-quality time-lapse video, the largest movie of the universe ever recorded. This movie will help scientists spot things that change over time, like asteroids, comets, stars that get brighter or dimmer, and exploding stars called supernovae. To create this giant time-lapse, the Rubin Observatory will have to use a lot of new technology. Some of its parts were invented from scratch, and others were improved versions of older designs. It'll help scientists discover all kinds of things. Many we already expect, and many we can't even imagine yet. Even so, Rubin Observatory was built with 4 main science goals in mind: learning more about dark matter and dark energy, creating a complete list of objects in our solar system, mapping the structure of the Milky Way, and studying objects that move or change brightness over time. Everything about the telescope, its huge size, fast scanning speed, and ultra-sensitive camera, was designed to make discoveries in these 4 areas as complete as possible. Rubin's telescope isn't the first telescope with a mirror about 27 feet wide, but it is the first to combine its primary mirror and tertiary mirror into one single surface. Putting both mirrors together is a special innovation that makes the entire telescope more compact. Because of this, it can move faster and get ready for its next observation much more quickly. The telescope's LSST camera is the biggest digital camera ever created. It's about the size of an SUV and weighs around 6,000 pounds. It holds a giant 3,200 megapixel CCD array. Just one single picture from Rubin is so large that you'd need about 400 Ultra HD TV screens to display it. It's also the fastest-moving large telescope on Earth. Rubin's telescope can swing into a new position in only 5 seconds and immediately start taking its next image. This speed comes from the telescope's compact design, thanks to its 2-in-1 mirror and its powerful drive motors. They can quickly move and stop the 220-ton telescope mount without shaking it. Even small vibrations can ruin an image, so this stability is a huge achievement. By the way, if the telescope were spinning at full speed, you wouldn't be able to outrun it. Also, Rubin Observatory has a rare combination. It can collect a lot of light and capture a very large area of the sky in a single picture. This means it can spot faint objects spread out over a wide region without needing many separate images. When you add the telescope's incredible speed, you get the perfect setup for creating Rubin's ultra-high-definition 10-year time-lapse of the universe. A fun fact, each Rubin image covers about 10 square degrees of sky. That's the same area as 45 full moons, or about the size of a golf ball held at arm's length. Another cool thing is that Rubin data will be immediately available to scientists in the US and Chile, and to members of Rubin's International In-Kind program. They'll be able to access everything through an online portal, which means that no giant downloads are needed. After 2 years, the entire world will be able to view Rubin data. Rubin will also process new images every night in near real time. If something in the sky moves or changes, the system will send out a public alert within 60 seconds. This will allow scientists to respond quickly and point their telescopes at the event. Each night, Rubin Observatory will create 20 terabytes of data and send out up to 10 million alerts about changes in the sky. By the end of the 10-year survey, Rubin will have produced a whopping 60 petabytes of raw images. It'll be the first time so much astronomical information is shared with so many people.